All right, so here is electron configuration again in another way. So we're just going to keep listening to this until it all falls into place and it makes all the sense. So electron configuration, remember, this is just how we are arranging electrons on atoms. We're trying to figure out if I've got the nucleus here, where are my electrons? Are they here? Are they here? Are they over here? So electron configuration is just about trying to predict the location of electrons around an atom. And we care about where those electrons are because their properties, how these elements bond to each other, depends on where those electrons are. So we're going to spend a lot of time talking about these electron configurations, electron arrangements. So we briefly went over this in class today, Thursday. Just a quick review. So we have 3 rules to figure out where electrons are, what their configuration is. The first one is the Aufbau principle that simply says that electrons have to go to the lowest energy levels first. Pauli exclusion principle says we can only have 2 electrons in any one orbital, and they have to have opposite spins. So we show those spins with arrows, one pointing up, one pointing down. So those are rules 1 and 2. Rule 3 is kind of weird. It makes more sense after we've done some practice problems. Hund's rule says that if we have orbitals with equal energy, and remember that our s orbitals are like just a sphere, but those p orbitals, they can be x, y, or z dumbbell shapes. And so there's actually 1, 2, 3 different p orbitals in each sublevel. So that means that those guys, those p's, would all have equal energy. And so we're only going to put 1 electron here, 1 electron here, 1 electron here. And then once each of those 3 have 1, we'll add the other one, the other one, the other one. Hund's rule, it's weird. It'll make more sense, I promise, when we do the practice problems. Speaking of practice problems, we again did these in class. Here they are again, just in case. So hydrogen has 1 electron. We're going to put it in the lowest energy level first. That's the Aufbau principle. 1, energy level number 1, is the lowest of 2 and 3. So I'm going to put energy level number 1 electron. And I'm going to show it with an arrow. This is the electron configuration of hydrogen. There's 1 electron, and then our arrows are electrons. 1 electron in the 1s orbital. That's it. Helium has 2 electrons. We're going to put them again in the lowest possible energy level. 1, 2. Just like that. This is helium's electron configuration. 2 electrons in the 1s orbital. Lithium has 3 electrons. How about 1, 2, 3? No, we can't do that because Pauli exclusion principle says that there's space for only 2 electrons in each and every orbital. So I cannot put 3 into that 1 orbital. Instead, I'm going to have to put 1 over here. So this is an orbital. It has 2 electrons. It's full. Electron number 3 is going to have to move over here to the next available energy level, the 2s. Beryllium has 4 electrons. I'm going to put 1 and 2 and 3 and 4. I do have space for 2 electrons here, so I can put those 2 into the 2s for beryllium. Beryllium's 4 electrons. 2 of them are going to be in the 1s orbital in energy level number 1. The other 2 electrons are going to be in the 2s orbital in energy level number 2. We're going to skip to carbon. Carbon has 6 electrons. We're going to go 1, 2. Whoa, I just drew half an arrowhead. Totally okay. Chemists are lazy. Sometimes they only draw half an arrowhead. 1 electron, 2 electrons. 3 electrons, 4 electrons. 5 electrons. Should I put number 6 here? No. This is where Hund's rule comes into place. So we know that these 1, 2, 3 different orbitals are all in the 2p sublevel, which means that these guys all have equal energy. And so rather than pack 2 electrons into the same little space, I'm going to go ahead and let them spread out. So these are carbon 6 electrons. 2 are in the 1s orbital, 2 are in the 2s orbital. I have 1 and another 1, both in 2p orbitals, but not the same 2p orbitals. Remember again that the p, these are the guys that go x, y, and z. So I have 3 different little clouds that are very similar to each other in the 2p sublevel. That's carbon. Oxygen. Oxygen has 8 electrons. We're going to go 1, 2, 3, 4, 5, 6, 7. Should I go here to 8? No, because the 3 energy level is bigger than the 2 energy level. I haven't actually filled the second energy level yet. I have 1 electron in each of these, but there is space for 2. I'm going to go ahead and put electron number 8 right there. So this is the electron configuration of oxygen. There are 2 electrons in the 1s orbital, 2 in the 2s orbital. 1, 2, 3, 4 in the 2p orbitals. They're spread out. Neon has 10 electrons. I'm going to put 1, 2, 3, 4, 5, 6, 7. I can't go here yet. I need to fill in these guys first. 8, 9, 10, and we're done. So this is the electron configuration of neon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8, 10. 2 electrons in the 1s orbital, 2 in the 2s orbital, 2, 4, 6 in the 2p orbital. Let's do sodium. It's 11 electrons on a sodium atom. 1, 2, 3, 4. We're getting good at this, right? 5, 6, 7. We need to go back and fill in 8, 9, 10. Where's electron number 11 going to go? Yes, right there in the 3s orbital. So this is the electron configuration of sodium. 2 electrons in the 1s orbital, 2 in the 2s orbital, 6, 2, 4, 6 in the 2p orbitals, and only 1 in the 3s orbital. So sometimes we draw the Aufbau diagram. This guy is the Aufbau diagram. And what's kind of nice is that it shows us that energy level number 1, the 1s orbital, has the least amount of energy, and energy level number 2 is next. And then next we have the 2p, and next we have the 3s, and then we have the 4p, and then we have the 4s, and then we have the, what madness is this? How do we go from 1, 2, 2, 3, 3, 4, 3, 4, 5, 4, 5, 6, 4, 5, 6? What madness is this? Remember in a couple nearpods ago, we were talking about here's the nucleus, here's energy level number 1, energy level number 2, number 3, and they get closer and closer to each other. Here's something crazy, starting at the top of energy level number 3, and the bottom of energy level number 4, top of 3, bottom of 4. They're so close to each other, they start to overlap. And so we actually have a little part of 4 that has less energy than the top part of 3. And here you can see again that I have 5 overlapping with 4 and 6 and 7. It's a hot mess up there because those energy levels are getting closer and closer to each other. They start to overlap. So every time we have anything bigger than 3 feet, 3p, I'm going to give you this diagram. And just remember that you go from the bottom, this is the lowest energy, we fill this guy first, and then next, and next, and next, and next, and next, and then just find those layers, what's next, what's next, what's next, 6s, 4f, 5d, 6p. Aufbau diagram. So we're going to use that Aufbau diagram to do a little bit more practice. So lithium, we decided, was up, down, up, because lithium has 1, 2 electrons in the 1s and 1 in the 2s. 1, 2, 3 electrons. Instead of drawing a bunch of arrows all the time, we can kind of summarize with this electron notation, electron configuration notation. So what's happening here is this. The 1s orbital has 2 electrons. And the 2s orbital has only 1 electron. Let's try with beryllium. You know that beryllium is Be. You know that beryllium has 4 electrons. 1, 2, 3, 4. So I would write that the 1s orbital has 1, 2 electrons. And the 2s orbital here has 1, 2, 2 electrons. Let's do boron. Boron has 5 electrons. Boron is just a B. 1, 2, 3, 4, 5. This is the electron configuration of boron. 2 electrons in the 1s orbital. 1s2. 1, 2 electrons in the 2s orbital. 2s2. 1 electron in a 2p orbital. 2p1. How about carbon? 6 electrons. Carbon's a C. 1, 2, 3, 4, 5, 6. There's 2 electrons in the 1s orbital. 1s2. 2 electrons in the 2s orbital. 2s2. 1, 2 electrons in 2p orbitals. Do I need to separate them? No. 2p2. Even though they're in different parts of the 2p sublevel, we're still just going to count them all up. There are 2 in the 2p sublevel. Feeling good? Kind of fun? Let's do iron. So find iron. He's a transition metal. He's in the middle. He has 26 electrons. 1, 2, 3, 4, 5, 6, 7. Remember Hund's rule, we have to spread them out. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. This is the electron configuration of iron. These are all the different energy levels and the orbitals where we can find electrons on iron. Let's write it as in notation form. So 1s has 2 electrons. 1s2. 2s has 2 electrons. 2s2. 2p has 2, 4, 6. 2p has 6 electrons. 3s has 2 electrons. 3p has 2, 4, 6. 3p6. 4s2. And then weird, 3d comes after 4s. 2, 3, 4, 5, 6. This is the electron configuration notation for iron. Let's do zinc. Zinc is just a couple after iron. Zinc is 30 electrons. I could totally erase and start all over, or I could just add what's new. So I'm going to leave these red guys. This is the first 26 electrons. I'm going to add number 27 so I can get up to zinc's 30. So 27 needs to go right here. 27, 28, 29, 30. So zinc is going to look a lot like iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 2, 2, 4, 6, 8, 10. 3, 10 is zinc. This is the electron configuration notation for zinc. All right, let's do argon. Argon has 18 electrons. We're going to go a 1, a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is argon. Argon has 18 electrons. Argon's electron configuration notation, 1s2. There's 2 in the 1s. 2s1, 2, 2s2. 2p, 2, 4, 6, 2p6. 3s1, 2, 3s2. 3p, 2, 4, 6, 3p6. This is argon. Let's do potassium. Potassium has 19 electrons. Do I need to erase and start all over? No. 2, 4, 6, 8, 10, 12, 14, 16, 18. Where's number 19 going to go? Right there. So I can rewrite potassium. 1s2, 2s2, 2p, 2, 4, 6, 2p6, 3s2, 3s2, 3p, 2, 4, 6, 3p6, and then our new one, 4s1. Notice that all of these guys of argon are also in potassium, because potassium has all the same electrons that argon has, just one more. So potassium has everything that argon has plus one more. So sometimes we write a shortcut, and so instead of writing all of that, I can say everything that argon is equal to, plus 4s1. The only thing that I can put in these brackets are noble gases. So think about on your periodic table, think about where those noble gases are, all the way to the right. Those are the only elements that are allowed to go in those brackets. So our shortcuts, we can only use noble gases. To figure out what noble gas to put in here, we're going to go backwards in the periodic table. So I'm going to look at potassium. It's number 19. I go backwards. 19, 18. Hey, 18 is argon. It's our noble gas. Argon 4s1. So potassium can be all of that, or argon 4s1. Cesium. Let's find cesium on the handy-dandy periodic table. Oh, it has 55 electrons. We really want to draw 55? No, we don't. So I'm going to find cesium on the periodic table. I'm going to draw a little periodic table over here. Cesium is second from the bottom in column 1. Cesium, number 55. It's in period 6. I'm going to go backwards to the periodic table and see if I can find a noble gas. 55, going backwards. 54. Hey, what's element 54? It's xenon. Xenon is a noble gas. So if I went all the way over here to the periodic table, xenon up here is 54. Go backwards to the periodic table. 55, 54 is xenon. So I can say that cesium is everything, those 54 electrons that xenon has, plus 1 more to get to 55. But where should I put it? Well, period number 6 means that we're in the 6th energy level. And we always start with S's. And there's only one. So this is the electron configuration of cesium. Xenon, 6s1. Xenon, because it's the noble gas that comes right before cesium. 6, because cesium is in the 6th period. 1, because it's the first guy in the period number 6. All right, so we are just about done, my friends. What is wrong with this picture? Whose rule are we breaking? That would be the Aufbau principle, because we did not fill the lowest energy levels first. This guy really ought to be over here. Good. That's all I have for tonight. See you tomorrow.